All right, in the next portion of the lecture, I'm going to talk about how meta-reinforcement learning can be framed as a kind of partially observed Markov decision process. And this perspective of meta-RL will help us devise new algorithms that have some interesting properties. So, at first this might seem a little odd, but the fact is that meta-RL can be viewed quite consistently as a partially observed MDP. So a regular MDP is defined by a state space, an action space, transition probabilities, and a reward. A partially observed MDP augments this with an observation space O and an emission distribution E that describes the probability of seeing some observation given a state. All right. So here's the graphical picture of a partially observed MDP. And my claim is that meta-reinforcement learning corresponds to regular reinforcement learning, but in a partially observed MTP. So take a moment to think about this. Let's say that you have a collection of meta-training MDPs, M1 through Mn, and you'd like to construct a partially observed MDP such that maximizing the reward in that partially observed MDP is the same as adapting to a new, fully observed MDP from your meta-training set. How could you do this? Well, in order to do this, all you have to do is construct the partially observed MDP. So the only thing you have to choose is the states and the observations and the emission probabilities and the dynamics. You don't really have to choose the action space because the action space is going to be the same. So the question really is, how do we embed a meta-RL problem into a POMDP? So in a POMDP, the policy acts on the observations O, right? And this typically requires either explicit state estimation, so maybe you might have some separate state estimator that estimates P of ST given the sequence of past observations, or policies with memory. Well, now that's interesting. We saw policies with memory when we talked about RNNs for meta-RL. So here's how we can think about this. In meta-RL, let's say that we represent our policy as pi theta of A given S comma Z. Previously I used phi for this, but I'm going to use Z instead of phi here for reasons that will be more apparent later. So Z here encapsulates in all the information the policy needs to solve the current task. So if that's the case, then learning a task simply corresponds to inferring Z. And you infer Z from your context, from your sequence of states, actions, next states, and rewards. This is in fact just a POMDP. So before we had an MDP with states SA, transitions, and rewards. Now we have a POMDP that I'm going to call M tilde with a modified state space S tilde and a modified observation space O tilde. The modified state space, so this is the true state of the system, consists of the original state space and Z. Because if you know the state and you know Z, you have everything you need to solve the task. Right, so this is S tilde. The observation consists of only the state. So you don't know what Z is, you have to figure out Z. So the key idea is that solving the POMDP M tilde is equivalent to metalearning. Because in order to solve this POMDP, you have to explicitly or implicitly figure out what Z is, and then take the optimal action in the resulting POMDP. So this is how you can embed metalearning into a POMDP problem. And this is why RNNs can do metalearning. Now, this might by itself not be such a great and useful observation because POMDPs are a lot harder to solve than MDPs. So the joke, this is due to Leslie Cabling, one of the pioneers of studying POMDPs, is that if you have a difficult problem and you turn it into a POMDP, now you have two difficult problems. Okay, so solving this POMDP requires either explicit state estimation, which is to estimate the probability of ST given your history of observations, that is to say, estimate P of Z given the history of observed states, or policies with memory. And we already saw how policies with memory, all these RNNs, can in fact perform metalearning, and that means that they are indeed solving this POMDP. But let's talk about the other approach. Let's talk about how we can do this with explicit state estimation. And it turns out that that leads to a pretty interesting class of probabilistic metalearning methods. So what we need to do in order to apply this idea is to estimate P of ZT, given a history of states, a history of actions, and crucially also the rewards. So the rewards are also included as part of our observation. If we can estimate this, then we can explore via posterior sampling. So if we have a distribution over z's, we could sample from that distribution and act as though that was the optimal z, and this corresponds to a posterior sampling exploration strategy. So the procedure is sample your z from your estimate p hat of zt given your past states, actions, and rewards. And this requires typically some approximation, for instance, using variational inference to learn the proximate posterior. And step 2, act according to pi theta of a given s comma z to collect more data. This is very much like the posterior sampling exploration strategy that we saw in the exploration lecture. And then repeat this process. Now, this is not optimal. Take a moment to think about why this is not optimal. What is something that this procedure could not do that you might want a learned exploration strategy to do? So it's not optimal, but it is pretty good, both in theory and in practice. So the reason that it's not optimal is because this procedure will not result in epistemic actions or information gathering actions. So when you sample a z from your posterior, you're sampling from your hypotheses about what the task could be and then attempting to perform that task. But the thing that you do to determine what the task is might be different from the thing that you would do for any individual task. So that's why this is not optimal. However, it is pretty good in practice, and there are good theoretical results showing that posterior sampling is an effective exploration strategy, and empirical results showing that it can work actually quite well if used properly. Okay, so here's a discussion of an algorithm that actually uses this idea. So this is an algorithm called PERL, which appears in a paper called Efficient Off-Policy Meta-Reinforcement Learning via Probabilistic Context Variables, and it uses variational inference to learn p hat. So you have a policy, pi theta of at given st comma zt, and you have an inference network, q phi of zt given a history of states, actions, and rewards. The objective for training the theta and phi, the parameters of the policy and the inference network, is the expected reward that you get from running pi theta using the z obtained from q phi, and the KL divergence between q of z and the prior p of z, which is obtained from the variational lower bound. So this is very much like the controls inference lecture. So you maximize the post-update reward, same as in standard meta-RL, and you stay close to the prior to ensure that q captures the uncertainty in the distribution. It's conceptually very similar to RNN meta-RL, but z now is stochastic. And the stochastic z enables exploration via posterior sampling. So here's a little animation showing this process. This is a 2D point mass navigation task. Each colored squiggle denotes a different episode rollout. The goal is the blue circle, and you could see that the policy essentially tries random potential paths. So all the goals for all the tasks lie on the semicircle. That's why they all go to the semicircle. And once it stumbles on the goal region, then it keeps going to the goal region and succeeding repeatedly. Okay, so one choice that you have to make in order to instantiate an algorithm like this is, again, to choose an architecture for q of phi of zt given the history. And just like with the RNN meta-learning procedures, there are many different choices for architectures that could all conceivably work. The particular architecture used in this paper encodes each transition SA S prime R with an encoder, and then averages together the features in a permutation invariant way to lead to a distribution over z's. There's an interesting fact here, which is that the history, the context, is actually permutation invariant. You don't actually need to know the order in which you observe the transitions, because within each MDP, the Markov property holds, which turns out to mean that the order doesn't matter. This particular kind of parallel encoder is particularly favorable, unlike an RNN, because you don't have to backpropagate through time for very long periods, because every every transition is only one step away from the final result. So the backpropagation paths are a lot shorter if you use this approach. But it's largely an architectural detail. Right. And then, of course, you have to pick an RL algorithm in order to perform this maximization. So PERL uses soft actor critic or SAC, but of course there are many other choices you could make, including policy gradients. These are the empirical results from the paper. The method works really well, but of course, a lot of the implementation details go into determining this kind of performance. Just to provide another data point from the literature, we can use this connection to POMDPs not just to derive meta-learning algorithms that use the special structure of this POMDP, but also to apply kind of more generic POMDP methods to perform meta-learning. So this paper called MELD uses state space models, very much like the models we discussed when we talked about model-based RL with images before, in order to perform meta-learning. So, as I said before, meta-learning can be viewed as a kind of POMDP, but it's kind of a special POMDP. So a regular POMDP has states, observations, and actions. Here the observations are denoted as X. This is a figure from the paper. And when we go to solve regular POMDPs, one of the things we could do is we could learn the underlying latent state space model. And we talked about this when we discussed model-based RL with images. So you might learn a latent state Z that explains the images, predicts future images, and it can be used as a representation for RL. In meta-RL, there's a little bit of additional knowledge. You know that the information in the latent state that is not observed is held constant over the course of the task. So you could say that there's a single per episode task ID T, which influences these Z's. And in principle, you would think that this structure should be useful, but you could also use just a regular state space model, simply adding the rewards to the observation, and this is what this procedure does, without really worrying too much about what the structure of the underlying POMDP is, and simply use the same state identification mechanisms that latent state space models already have to account for these additional task variables. Now this is ignoring a little bit of structure that we know actually does exist, namely that the task ID doesn't change over the course of an episode, but it turns out to be pretty easy to learn that structure, so ignoring that prior knowledge isn't so bad, and the added simplicity of just using generic state space models is quite appealing. And you could do this with images and so on, all the reasons why we prefer these kinds of models in the model-based RL section. So using this latent variable model generalizes meta-learning in POMDPs, and turns out to work very well as a meta-learning algorithm. These are some videos of a robotic arm inserting a cable into an Ethernet port from images, and it gets a reward if it inserts the cable into the correct hole. So you can think of this as like trying to plug the cable into the router and seeing which port is actually active. So it learns to perform this exploration strategy. Here's a simulated task that shows the gain in information. In this case, the red line shows the ability of the model to predict future rewards, which is well correlated with its ability to identify the task. And here the reward is obtained for pushing the right button, and what you can see is that the robotic arm kind of does this search strategy where it approaches each button and tries to gently push it to see which one gives it the reward before discovering the right one. All right, if you want to learn more about the connection between meta-RL inference and POMDPs, these are some of the potential papers that you could check out. And then in the next section, and then before I conclude this section, one of the things I want to do is go over the three perspectives on meta-RL, or at least model-free meta-RL, that we've covered before. So all three perspectives can be encapsulated by this kind of generic picture. And then we ask, what should f theta of MI actually do? It needs to improve the policy with experience, and it needs to learn how to explore. And the perspectives that we saw were the following. Perspective one, just train a big RNN with a standard RL algorithm, but with these meta-episodes, where each meta-episode spans multiple episodes. Perspective two was the bi-level optimization view, which is how we got these mammal algorithms. And perspective three is that it's just an inference problem, treat it as a POMDP, and then learn how to infer Z, which is the context that you need to perform the task. So the RNN view is conceptually very simple, and it's relatively easy to apply. It has a few downsides, though. It's vulnerable to meta-overfitting. RNNs are very powerful models, and if your training data set If your meta-training data set is not too large or not sufficiently diverse, which is actually often the case in reinforcement learning, you can meta-overfit, which means that you will do very well at recalling the meta-training tasks, but maybe not so well at generalizing to new tasks. And it can be challenging to optimize RNN models in practice with RL. The bilevel optimization view has a few advantages. It has good extrapolation, this is sometimes referred to as consistency, meaning that even if your new task is different from your meta-training tasks, because you're simply running RL, you're running something like policy gradient, eventually it'll learn the new task, even if it's not accelerated as much as it would be for in-distribution tasks. It's a conceptually elegant framework. It makes use of a lot of neat optimization ideas, and there's sort of a better understanding for why these approaches work. There's, quite a bit more theory studying these kind of bilevel methods than the RNN method. But it can be quite complex to implement because of the second derivatives, and it might require quite a few samples in the policy gradient case to train these kinds of methods, to meta-train these kinds of methods, that is. The inference problem view is simple and effective. It provides good exploration by posterior sampling. It has this elegant reduction to solving a special kind of POMDP, which gives us a good tool for designing new algorithms, but it's also vulnerable to meta-overfitting like the RNN approaches. And it can be challenging to optimize in practice because of the additional variance and noise due to the variational inference. Now that said, these three perspectives are in many ways not that different. Perspective 3 is really just perspective 1, but with stochastic hidden variables, if we sort of disregard the intellectual aspect of the POMDP connection. So you can think of perspective 3 as just one where you've renamed phi to z and added some noise. Perspective 2 is in some ways just a particular architectural choice for either 1 or 3. So you could use an RNN, you could use this PERL encoder, or you could use a gradient step. And in some ways, they're just different choices of architecture.